again, it's this low risk issue. So typically you're using technology that's 5 or 6 years too old because that's when you start the project, and then you get your funding for that and you have to stick to that. Low risk is low risk in cost and management and technical risk, which means that you're not going to change a design for the latest new Microsoft Vista, for instance. You're not going to switch to that on the fly. So that means that you're sort of working. So essentially, the development is new science ideas. You compete for the funding, and then the technology is essentially an improvement in what's done before. In solar, one of the things so the Solar Dynamics Observatory is a $1 billion mission almost, and their big breakthrough is really high resolution, high cadence magnetic field observations that will help us probe very deep into the sun through Halley seismology. Some of the advances that we're pushing and are going to happen in the next 8 years or so. Solar Probe Plus is an instrument that's going to get within 9 solar radii, which is quite a sunburn. And so a lot of the technology there is how you shield your instruments from that kind of intensity of photon flux or light, whatever you want to call it. We also have the Solar Orbiter, which is a European mission that's planned for 2017, 2015. And the thing there is it's going to go out of the ecliptic plane so that we can get an inclined orbit that can look at the poles of the sun to some extent. That sounds like it's trivial, but it takes a lot of fuel, a lot of energy, and a lot of planning to get out of the ecliptic plane. That's when you have all your energy, all your launch costs, and everything goes into that. So those are things that drive that kind of advance. It's not, here's this great new technology, here's this fantastic set of instruments, let's put it in space. It costs too much to do that. The last thing I'll say is that one of the biggest drivers of what you can get scientifically is telemetry. That's the thing that hasn't been pushed as much as the detector technology, the spacecraft technology, getting your data down, especially for somebody who's a solar physicist where there's more data than you need, if you like, but getting your data down when you're getting even a megabit per second, that's, if they can make some advances in that, that would be a huge deal for most of us, especially now that astrophysics is getting bigger telescopes, more data, and so on.
And we're throwing away most of the capital.
You have to be you have to be clever in how you packet the data, what you decide to send down. So you may be missing some really exciting stuff.
So how about the Hubble? How have the recent advancements or the upgrades that they recently did? How did that change what they had before?
Well, so Hubble has the main increases there have been in the sensitivity of the instruments. I mean, the basic telescope hasn't changed; it's the same aperture as it was before, and so forth. So the increases in technology there have been on the sensitivity side, and those increases have been in factors of 10 or more. So those are, I think, really good. The thing that, of course, is going to be so fantastic about the next generation space telescope is just the size of it. It's going to be, so Hubble is about a 2.4 meter telescope. This one's going to be about an 8 meter telescope. So it's just going to be a lot bigger telescope up in space. You get both the angular resolution and then the sensitivity of being above the Earth's atmosphere. But in terms of things that I think that are on the horizon and maybe relatively soon is going to be the development, technological development on the NASA side in terms of precision flying of spacecraft. Several years ago, there was a grand idea to build what was called the terrestrial planet finder, an instrument that would be able to find Earth-like planets in Earth-like orbits around stars and take pictures of them and ultimately spectra and look for signs of life. And the way they were going to do this was from interferometry. The idea is that by combining the signals from two distant telescopes, you can actually get the resolution of one telescope that is as big as the distance between the two telescopes. We do that on the ground all the time. We have a lot more control of the things that are on the ground. The idea was to do this in space, and in order to do that, you have to accurately know and maintain the distance between two spacecraft at the less than a centimeter level. And so, the terrestrial planet finder has been scratched due to budget constraints. But another thing that people are now talking about to use in combination with JWST, is coronagraph technology. If you can blot out the light from a star, you can look at what's around the star and find faint things like planets. You can do that within a telescope aperture, but there's always scattered light. There's always problems that makes it technologically a little bit hard to get really high contrast. But the idea is, well, if you can fly an occulter several thousand kilometers away from the next generation space telescope and have it sit in front of the star you want to look at, you can do the same thing almost perfectly. But that's going to require maintaining two spacecraft in a particular relative orientation for a long period of time. And that's a technological feat, but that is something that I think is probably on the next 10-year time scale that we will attempt and hopefully accomplish.
So you mentioned the cancellation.
Oh, yeah. To me, I think some of the exciting things that we've seen lately are going into orbit with Cassini around Saturn, of course, landing on Titan and seeing the escapes of methane lakes that we thought about but really had never dreamed about until we saw them. It's just spectacular. Seeing the water jets out of Enceladus and understanding how it affects the magnetosphere of Saturn has just been something that's been really exciting. The whole idea of magnetic reconnection and how important it is on the sun, on the Earth, and pulsars and stellar jets. And my graduate student last year got the outstanding thesis Oak Prize for really flying cluster right through a magnetic reconnection line, an X line, and seeing how the magnetic fields are different on either side of the X lines. And we're going to be doing the next generation of that with MMS. So these are the kinds of things, to me, being someone who likes to look at in situ data, we have theories and models of how things can work and how they should work and how we think they're going to work. But the most amazing thing about going to every planet we've been to is that we've been surprised. So that's why I prefer to be a data analyst than a theorist, because sometimes the surprises are unpleasant, but they're always fun. I mean, that's what really makes science fun, is learning something that nobody else has ever known before. And that's, to me, why I'm a scientist.
So how do you think the commercialization of manned spaceflight will affect space science? Or do you think it'll have any effect, or none at all?
Potentially it can have a huge effect. I mean, one of NASA's big problems at the moment is the manifest of an adequate set of launch vehicles. You can get light spacecraft, Taurus-type missions, and Pegasus-type launches, which are these basically missiles that get dropped from an airplane and then take off. Those can get you so much mass into space, but not a lot, maybe 100 kilograms, 200 kilograms. They used to have Delta IIs, which would then get you the next setup. I think the last I heard when we got the report from that was that there was maybe 4 of those left, and they're all earmarked for some mission or other. The next one is Delta IV, and that can launch something like 1,000 kilograms or some huge amount, but the cost is still, per pound is still the same. So if you want to fly a small mission, it's very difficult to actually get a launch vehicle to get that small mission up, and so the cost will go up. Commercialization can help that, because it's good and it's bad. It's good in the sense that they're launching 1,000 kilogram telecommunication satellite. You can adjust the ring that they have in there, and you actually, some of these missions have flown bricks, literally flown dead mass, pieces of lead and all sorts of stuff. Because they need the ballast, or they need the balance, or whatever. If you design the adapter ring properly, you can actually put a spacecraft on there, and you can get your launch. Now the problem is, how do you get rid of that without affecting the moneymaker, which is the telecommunication satellite? So those are issues, but they've all been solved and can be done. So in some senses, having access to large launch vehicles to launch small missions helps you, because now you can get the money to build a $200 million or $100 million mission, which is a small mission, and have it launched, as opposed to having a $100 million mission that costs $1 billion